Hello. In the last segment, we looked at a simulation in which we did repeated trials of n coin flips. We saw that as n got larger, the ratio of heads to tails became similar across the trials. Eventually, for each of the trials, the ratio was quite close to 1. That's to say, close to half the flips came up heads and half tails. I observed that this should lead us to conclude something about the next flip, that heads and tails are about equally likely. But why did I think I could conclude that? That's the topic of this segment. What I was depending upon is something called the law of large numbers, also sometimes called Bernoulli's law. So, contrary to many people's views, the law of large numbers have nothing to do with really big numbers like this. What it really tells us is that in repeated independent tests with the same actual probability, and by the way, we have no idea what that is, p, of a particular outcome in each test, the chance that the fraction of times the outcome occurs differs from p converges to 0 as the number of trials goes to infinity. By the way, this handsome fellow here is Bernoulli. It's worth noting that the law of large numbers does not imply, as too many seem to think, that if deviations from the expected behavior occur, these deviations are likely to be evened out by opposite deviations in the future. This belief is something known as the gambler's fallacy. It's nicely illustrated by thinking of the game of roulette. For those of you who don't know the game, it starts with the wheel, and one drops a little ball in the wheel, gives the wheel a spin. Eventually the wheel stops spinning, and the ball settles in one of these slots. Most of the slots are either black or red, a few are green. For the moment, actually for the rest of this segment, let's ignore the green slots and pretend that they're all either black or red. If the wheel is fair, half the time the ball should come to stop in a red slot and half the time in a black slot. Despite this probability, an amazing thing happened, as reported by Huff and Geis in their book, How to Take a Chance. I quote from that book, "On August 18th, 1913, at the casino in Monte Carlo, black came up a record 26 times in succession. There was a near panicky rush to bet on red, beginning about the time black had come up a phenomenal 15 times. In the end, the unusual run enriched the casino by some millions of francs." So let's think about what was really going on. So once red had come up 15 times in a row, the supposedly smart gamblers said, "Wow, that's a surprise. How often should that happen?" Well, about 1 out of 32,000 times. Pretty unlikely. And they said, therefore, we're going to have to eventually have the same number of blacks and reds. So in order to even it out, we're going to need to see more blacks in the future. I better bet on black. Well, once red had come up 25 times in a row, people did the probability and said, well, the chances of that are about 1 in 33.5 million. Really unlikely. And said, what's the chance of 26 in a row? 1 out of about 67 million. Well, that they thought was highly unlikely, hence the stampede to bet, hence the extra profit for the casino. So what was wrong with this logic? Well, it's true that if you started with no spins, it would be perfectly reasonable to say the probability of getting 26 reds in a row was 1 out of 67 million. On the other hand, if I already have 25 reds in a row, what's the chance of getting 26 reds in a row? Exactly the same as the chance of getting red on any one spin, that is to say a half. And the reason for that is that these were independent events. When we think about the law of large numbers, we should also realize that large is a relative concept. Imagine flipping a fair coin on the order of 10 to 1 million times. That's kind of hard to imagine. Your thumb would get very sore if you did that, but pretend you could. If you could do that, you would expect to encounter several sequences of 1 million heads. Now, if you were to only look at those subsequences where you saw 1 million heads in a row, you could easily reach the wrong conclusion about the coin. So you can't just look at a subsequence of a very large random sequence. You have to look at the whole thing to reach any conclusion. In fact, if every subsequence of a large sequence of events appears to be random, it's highly unlikely that the sequence itself was generated by a random process. If your iPad shuffle doesn't play the same song twice in a row, at least once in a while, you can bet that it's not really random. Finally, notice that in the case of coin flips, the law of large numbers does not imply that the absolute difference of heads minus tails converges to zero. In fact, the more flips we do, the larger we can expect the absolute difference to get. What converges is the ratio. Now let's look at a small function that illustrates the law of large numbers at work. The function flip plot takes two arguments, the minimum exponent and the maximum exponent. It initializes some things to the empty list. It then builds the x-axis for what we're going to plot, that is to say the number of flips we're going to experiment with. And it looks at all flips in range from minimum exponent 2 to the minimum exponent to 2 to the maximum exponent. So it will try, let's say if the minimum exponent were 4, 2 to the 4, 2 to the 8, 2 to the 5, 2 to the 6, 2 to the 7, etc. So the number of flips will grow exponentially. The first thing it does is, after building the possible x values, it then goes through and conducts the experiment. For each value in x-axis, it will flip that many coins and keep track of the heads and tails and the ratio of heads to tails. Finally, it will produce a couple of plots with appropriate titles and labels for the axes. Let's run it and see what we get. We get two figures, and let's go over and look at those figures in the PowerPoint so that I can draw on them. The first figure plots the difference between heads and tails. If we look at it quickly, it seems to suggest that the absolute difference between the numbers of heads and tails fluctuates at the beginning, crashes, and then steadily rises. However, we should be careful before we believe that, because what we have to keep in mind is that in fact we only have two actual data points to the right of x equals 300,000. We have this point and this point. We happen to have connected them by lines which could mislead us into thinking we have a trend, when in fact all we have is isolated points. The moral here is whenever you look at a plot with this kind of lines, ask how many points it actually contains before jumping to any conclusion. Looking at the next plot, what we see is that mostly it appears to be a flat line. Well, this too is deceptive. In fact, there's a fair amount going on over here on the left, but it's hard to see. The reason it's hard to see is that we have enormous dynamic range here on the x-axis, as we did in the previous plot, by the way, ranging from 0 up to 1.2 million. Not that much dynamic range in the y-axis. Therefore, action over here on the left side is very compressed. Fortunately, we can fix that. What we see with this kind of scaling is what's called linear scaling. That is to say, the points on both the x and the y-axis are evenly laid out. The distance from 0 to 200,000 is the same as the distance from 1 million to 1.2 million. That makes it hard to see what goes on between, say, 0 and 100, or 0 and even 1,000. Fortunately, all these problems in exposition we've talked about are easily fixed in Python. Let's go look at code that does that. This code is the same as the previous implementation of flip plot, except I've added some additional code at the bottom that provides us with different presentations of the same data. I want to emphasize it's the same data, just presented in a different format. So what I've done is, instead of drawing those lines, I've just plotted the points as blue circles so that we can easily see how many points we really have. Also, I've changed the x and y axis of the first plot to be semi-log x and semi-log y. We'll see what that means in a minute. And on the second plot, only to be semi-log x. And again, we'll see that in a minute. Let's run it and see what we get. Well, we get the same first two plots, and I won't bore you by looking at those. But let's look at plots 3 and 4. Let's look at plot 4 first. This is the heads-tails ratio. So notice that as before, the y-axis ranges from 0.5 to 1.3. There was not much dynamic range there, so there was really no reason to change it. But the x-axis is now logarithmic. So there are as many points between 10 to the 1 and 10 to the 2 as there are between 10 to the 5 and 10 to the 6. This allows us to see clearly what's happening on the left side of the plot where things are changing more quickly. So this plot suggests pretty strongly that the ratio of heads to tails converges to 1 as the number of flips gets large. That's a good thing. Let's look at the other plot. Here's figure 3. Once again, the x-axis is logarithmic, but now I've also made the y-axis logarithmic. Because there was so much dynamic range there, we couldn't really see what was happening down near the lower left-hand corner. It now emerges as if there is a trend, clearly not a perfect trend, of the absolute difference between heads and tails growing with the number of flips. We can be a little bit suspicious because it bounces up and down, but the trend is, I think, pretty clear. Okay, let's wrap this segment up with a couple of observations. Perhaps most importantly, we should point out that it's never possible to be assured of perfect accuracy through sampling unless you sample the entire population. I want to emphasize the word assured. You might actually get the accurate answer, but you can't know it's an accurate answer without sampling the entire population. And of course, for coin flips, where we're speculating on an infinite number of flips, we can't do that. And in fact, in most cases, you can't sample it. One might flip a coin twice and get one head and one tail, and conclude from that that the probability of getting each is a half, because that's what you got with your two flips. Well, you'd have the right answer, but you would have gotten there through totally bogus reasoning. What we'll talk about in the next segment is how many samples we need to look at before we can have some justification that the conclusion we're reaching really is sound.